Thank you. So my name is Stephan Chenette. I'm a security researcher at Website Security Labs. We're based in San Diego. And to give you an idea of my role there, it's always been one that I look at the technology that exists and I try to see the next generation of attacks. So to give you an example, I was part of a research team where we had a host intrusion prevention system looking at in-memory exploitation and that detection of exploits. So my role was trying to create exploits that perhaps didn't follow the general rules and general guidelines and would bypass that type of detection. I worked at an antivirus company where they were putting and employing certain heuristics for malware. So I would write certain types of malware to try to evade that detection. Right now I'm at WebSense, and the big thing that we're doing is real-time content analysis. So that's web content going from a malicious web server down to the client, being able to detect that. And so my role is to try to create the perfect scenario. As an attacker, how do I create a malicious website to evade that type of detection? Not only gateway detection, but desktop detection as well. So what I'm presenting today is an attack I call Script Fragmentation, and I want to share some of those details. So the agenda is that we're going to be talking about web exploit delivery, how it currently exists. We're going to be talking about how attackers on a day-to-day basis attempt to bypass any detection that's put in place, both on the gateway and on the desktop. And then what we're going to talk about is next generation exploit delivery. One of those techniques is script fragmentation. So again, I'm talking from the perspective of an attacker, but obviously this is beneficial to everyone, network administrators, users. You'll gain a kind of an understanding of how a lot of software companies are creating the detection, and prevention on gateways, on desktops of malicious web content. And how, from my perspective, we're looking at perhaps what we're going to see down the road on a more common basis. So let's talk about exploit delivery, and which is a large part of successful web exploitation. So in order to have successful web exploitation, if you have a vulnerable service or application, you found your vulnerable service, in order to create an exploit for that service or application has to be active, has to be accessible. You have to have an exploit that's reliable, that's harder done than said. Heap spraying is actually not that reliable, where some of the design bugs are 100% reliable. And then you have to be undetected. And what does that mean? That means really two things. You have to be undetected if you have a user going and visiting a malicious website, from that malicious website into the memory of the browser or the memory of the ActiveX control or whatever process is perhaps running. And then you have to be undetected once you're in memory of actually executing that exploit. So, bypassing any of the common functions that are hooked, common instructions that are kind of referenced. We're going to be talking about the first one, which is how do I get my exploit from point A to point B completely undetected? So a successful evasion really has to do with passing content over the network that is indistinguishable from benign traffic. And if it's not indistinguishable, it's completely, you're not going to be able to process it. And the gateway or the desktop is going to fail open. It's going to allow it to pass through. So right now, when attackers are creating malicious web pages, malicious websites, there's a lot of currently employed techniques. From the network and other perspectives, they're always looking as to where those users are coming from. They have a commonly shared blacklist of all the security company network addresses. So they're blacklisting a lot of security companies. They are perhaps just serving that content only once. So if you did have rotating IP range and you were going to check that malicious content, and you were assuming that it was always going to be there, you might get it the first time, you won't get it the second time. And they're even, with Storm, for example, you'd go get it and you'd go get it multiple times, and then they DDoS you. So they have defense mechanisms in place. Fast fluxing is very commonly used. And they're also verifying that it's a browser going to visit their malicious website. It's not a crawler. There's thousands of ways to tell the difference between a crawler, not only like a Google crawler, but actually most security companies have a crawler that they've built in-house, going to visit all these malicious web pages, pulling down the content and to determine what's happening. So they're differentiating between a real browser and that particular crawler. But most importantly, for the content, they're obfuscating the content. They've moved one step past that. They're using polymorphic obfuscation, and in the last year or two, they've more and more used encryption within various parts of the content being passed down. But still, they're really in kind of an old school mentality. And when attackers are making use of the web in general, from a content perspective, they're really in a Web 1.0 world. And let's talk about what that means. So there's kind of a shift in mentality that needs to happen within a lot of people who are looking at protection on the web. Common scenario, get HTTP OK. So when I go and fetch a page, let's assume that it doesn't have a lot of other images, a lot of objects within that page. It's kind of a get and then a response. Web 1.0 world, it's synchronous. Click, submit. If we all remember kind of, you know, before kind of a lot of the more mashups and everything, you'd go to a forum, you'd fill in all the information, you'd hit submit. What would happen? You would wait forever and ever and ever. It was processing on the server. Finally, something would come back, but it was really synchronous. It's not really how it is today. Web 1.0 world, from the perspective of a lot of security companies, is still kind of how they're viewing things. Do a get the response. What happens? The response comes back in its complete 100% of the content comes back all at once. And in most cases, if it's a gateway looking at it, it's going to inspect it in line, somewhere along the line, and it's going to have a lot of content to look at. It's easily going to see that, for example, this is one of the VML exploits. It's easily going to tell there's certain keywords, shell code. You know, this is everyday kind of signature detection. It's easily going to tell that there's a simple NOP sled, 1990s at the beginning. It's going to be able to tell that there's a use of a heap address within that unescape. So there's things that are just going to trigger automatically. I mean, bells and whistles are going to go off like crazy. This is obviously malicious from any of the most simple signature analysis engines. And from the desktop perspective, well, most desktop AVs are looking at the cached file on disk. They're also looking at the network, like the gateway is doing, but they're also looking at the cached file on disk. And so that exists normally in the C document settings, whatever your username is, local settings, temporary internet files. That pops on a disk, hits disk. They're going to use their common AV engine to match one of thousands of other signatures, the same way a gateway is going to do it, to determine if it's malicious. So it's one-step content transfer. Look at this big blob of text. I have more than enough from a defense standpoint to determine if it's malicious or not. So what did attackers do? Next step, they started using obfuscation, polymorphic obfuscation. Every single time a user would come to visit that site, not only would they be fed content that was completely obfuscated, scrambled, difficult for a signature detection engine or a simple signature detection engine to process. They started using polymorphic obfuscation. It would be completely dynamically generated when that user would go to the site just for them. If you've never looked, because I can't assume that everybody loves to look at malicious content all day long, this is what it commonly looks like. You know, it's completely scrambled code. This is what's going to be fed from that malicious server to the user. You know, you can't make much of this. The characters, the variable names are obviously a little bit higher entropy. For example, white space for the most part is removed. What we're looking at here is a simple substitution cipher. So they've created some string. It's got a long text of some type of rotated character. It's going to be fed through an algorithm, and it's going to make sense on the other end. Most likely eval will be called, and then it'll be processed normally by the JavaScript interpreter. But looking strictly from a signature analysis standpoint, there's not much sense you can make out of it. It's the same as when you look at an executable. 80–90% of malicious executables are packed. Packed doesn't necessarily mean malicious. Same is to be said of obfuscated content. There's a lot of good websites that are using obfuscation. Safari books, a lot of copyrighted material. There's many, many reasons why you want to, in this day of age, paying a web developer $100,000 to develop a website, why you'd probably want to obfuscate that content. A simple measure to try to protect your information. So obfuscated malicious content, it's removing white space, renaming variables, renaming functions, adding anti-debugging measures, encoding values, multiple things to normally just scramble that code. Obviously on the malicious side of things, they're going to do a little bit more and try to add some anti-debugging measures. So once attackers started to do this, which is something that happened quite a while ago, the obfuscation response from many security companies were that they started to create simple JavaScript engines within their products. I mean, before they started creating it in their products, you probably heard that most of the researchers, myself included, started presenting on, JavaScript research tools that you could use, kind of variations of SpiderMonkey. SpiderMonkey is from Mozilla. You can tweak it to kind of have it dump out the deobfuscated content once you would implement various things that were missing. That was later taken, and security companies started taking SpiderMonkey's code as well as their own implementations of a JavaScript interpreter and putting it into products. The other thing that they would do, and this is very much similar to how packers for malicious executables were dealt with, is that they started looking at the deobfuscation algorithm. It's the same way with malicious executables. They started looking at the unpacker routine. Jump to the entry point, look for the unpacker routine. This might be something that it's FSG, it's mu. It's not something that's typically thought of as a good executable because it's packed with something that no good executable is packed with. Well, the security companies thought the same of many of the deobfuscation algorithms. Dean Edwards Packer is very commonly used. That's not one that would have a signature, but a lot of the custom algorithms that were used to create this deobfuscated content or obfuscated content and then deobfuscate it were targeted in terms of a signature. But for the most part, many of the simplistic JavaScript engines that were put in these products are easily bypassed. They just don't implement enough of the functions. They have to keep up to day-to-day to act just like Firefox, just like IE, and most of those engines are not doing that. Simplistic first response, first thing that was really implemented from the attackers. So what did attackers start to do next? And this is what we're going to start to talk about, is where are we seeing the trend going up till we're going to talk about the next generation of how exploit delivery is happening. So the next thing that started to happen was multi-part attacks. So attackers said, fine, you're looking at the entire blob of content. In this example, it's not obfuscated. It's the same example as we saw at the beginning. But I'm not going to allow you to do that. It's too simple. You're looking at my deobfuscation algorithms. You do have a JavaScript engine of some sort. So you're not going to do that. What I'm going to do is I'm going to send a multi-part response. Multiple connections. So let's see what that means. So this is taken from an example of a live malicious page. It's a little bit of JavaScript. And on the top, it's not really obfuscated, but it's using some ASCII characters to make it look a little bit difficult for human reading. But on the bottom, I kind of remove those ASCII characters to make it a little bit simpler to read. And all it is this dynamic creation of an iframe. Now, when a page has an iframe inside of it, that just instructs the browser to go and fetch that content. So you've made a separate connection after your initial content has come down. So the iframe that's fetched is, and don't go visit this website because it's probably still live, cu.org.cn. So let's see what's on that site. So we go to that iframe, we look at the content that would be fed to the browser, and that iframe then again holds more iframes. 123.html is one example of one of the iframes in there. Let's look at that. Go to that iframe. It contains, well, it's the same thing almost as an iframe. It's a script tag, and it's going to fetch 1 through 11.jpg. 11 separate files that it's including. It really doesn't matter what the extension is. The browser is going to treat it the exact same. So if you look at each of those files separately, 11 separate files, you'll see that each one of those contains a piece of the sum. So from the perspective of the content analysis engine looking in the middle, they're going to look at each separate one. But they're not going to look at it in total. This is a problem from, one, a JavaScript engine. So it's going to get var. Let's look at the first one. It's one.jpg, var, and then that variable name equals 0. And they'll say, great, I don't really see anything malicious from that. And they're not going to have 2.jpg because it's a completely separate connection to really put the pieces together. And then 3.jpg. They have typically a gateway will have under 1 millisecond to analyze content. 1 millisecond. So they're not going to keep state, especially of separate connections that, for all intents and purposes, they have no idea that are related. So 1.jpg, 2.jpg, 3.jpg. 3.jpg is a little bit more interesting. It's obviously got a bunch of shellcode in there. A signature analysis engine would pick this up. The JavaScript emulator is really where it would have the most amount of problems. So this is somewhat successful if they perhaps don't have the right signature. Again, polymorphic obfuscation. This was not obfuscated, but breaking it up into pieces, absolutely successful as a first kind of step. So current techniques. All right, let's recap. Obfuscation, highly used. I would say in 90 to 95% of all malicious web pages, what they'll do is they'll put an iframe. They'll compromise, hundreds of thousands of sites. We saw this with Gumblar, Beladen, 9ball. These are mass injections. Mass injections that either they were able to embed content on that site through some input validation that wasn't checked, or FTP credentials that were stolen due to infected laptop, had keylogger, same old scenario. But iframes are generally embedded onto that site, and finally, the landing page in most cases is an obfuscated page. 90-95% of the final landing pages will be completely obfuscated. They'll make use of encryption. So as we saw before in the multi-part response, in many cases, there might have been a key that would have been used in the algorithm that was included in a separate file. So there's several encryption algorithms that are used, especially in the multi-part, which is really what's used in the current techniques more and more, is breaking it up into multiple parts through an iframe or a script tag. But is there even more that attackers can do? So let's enter into Web 2.0. And Web 2.0 is a huge marketing term, but there's really a huge shift in the way everything is happening. It's more about the clients fetching content from multiple servers, servers retrieving content from the client. It's just a completely different way of how and where content's coming from and who it's actually coming, who's responsible for putting content up there. Gadgets, widgets, mashups, common terms in a Web 2.0 world, but it's a completely different technology. It's very much, as opposed to the Web 1.0 world, which is synchronous, click, wait, it's asynchronous. You have objects within JavaScript that you can use that are happening in the background, sometimes based off user actions, sometimes based off timers. But things are happening in the background. Content has been served down to the user, and multiple things can actually happen. And obviously, we know from the mashups and Gadget's top 100 websites, almost all of them are, one way or another using Web 2.0. So attackers in a Web 2.0 universe, when they are using any of these technologies, what are they using? So they've done a great job of exploiting user-generated content. You can right now create an eBay auction site, for example, which allows you to embed HTML in there. And if you've obfuscated it enough, you can actually embed an exploit in there. Create some simple auction with the best. Choose your best product, best Xbox, sell it for $5 at Christmas, and you can actually create a malicious eBay auction. Anybody who goes to visit there, they don't have to buy it. They can actually, they'll be exploited on the site. If it's not obfuscated enough, it'll be caught. Their team is pretty good in terms of constantly scanning the content that's on that site. Blogspot, multiple files every single day. It's still one of the top 10 sites that you'll find multiple malicious exploits hosted on Blogspot. They're making use of all the free accounts, free access, the trust factors within Web 2.0 to store content, more exposure to users. So they're doing a lot with Web 2.0, but they're not really changing anything in terms of exploit delivery. There's no change there. So let's talk about Web 2.0 exploit delivery. So this is really the core of my talk, is what is the next generation of content delivery. It's one technique called script fragmentation. And that's active content. You can do it with JavaScript. You can do it with VB script. And it's fragmentation, little chunks of data. So script fragmentation, in its most simplistic form, to explain it, is malicious AJAX, asynchronous JavaScript in XML. Doesn't have to be XML, by the way. That's just one choice of a data form. But it's malicious asynchronous communication. So fragmentation, it rings a bell, sure. TCP fragmentation, still a big problem on IDSs, IPSs. But what's the big difference? Well, TCP has an RFC that, if followed correctly at least, given fragmented packets, you can reassemble. There is some type of standard. When we're talking about script fragmentation, we're talking about the application layer. This is a completely custom layer. It's per application. You have custom applications. There's never really going to be ever a standard to what's happening on the application layer. TCP fragments, there is a standard. Script fragmentation, I can every single day create a polymorphic application to how my script and my web server are going to communicate. So application fragmentation. I can certainly use asynchronous communication. That's my choice. I'm going to be building custom protocols on top of the application layer. There's absolutely no standard because it's my application. Web apps are huge in terms of communications back to the client. And imagine the complexity and the power that you have from the perspective of the browser. The browsers are one of the few types of applications that will visit a completely anonymous site, download JavaScript, download VB script, which gets fed into memory, and execute it. You're just executing unknown code. And sure, there's a lot of things that JavaScript can't do. It's sandboxed, but there's a lot of things it can do. It's pretty powerful. I mean, we're going in memory and we can do things. I can, for example, embed, if I'm talking about some Stego techniques, I can embed content that I want inside of an image, and using kind of canvas within JavaScript, I can go and read bytes from that image. So I've somehow, another evasion technique, brought content together, read from various different files to do what I please with. JavaScript is a very powerful language, and it's going to become even more and more powerful. But the fact of downloading content and being able to just execute it is quite amazing, and that's why we're at where we're at with in terms of the web. But there's a lot of malicious things we can do. So let's see what we can do. And for that, what I'm going to do is, it's a quick lesson, but I want to involve everybody in terms of understanding this. I'm just going to go with some real quick basic JavaScript. So HTML, I'm hopeful that everybody already understands the basics. We're going to talk about real quickly what the browser document object model is, the DOM. We're just going to go over some basics of what you can do with JavaScript. I'm not going to really mention JSON. I'm going to show you what the XML HTTP request object is, something you use for remote request. And we're just going to touch on the X-domain request object, the cross-domain request object. So when you go and visit a website, let's just say that it comes down with the first of the top code, HTML body, div body, HTML. You have the notion of what's the HTML. The HTML is the top. What's the DOM? Well, that's the memory representation of that initial HTML. So at the basic start, they look identical. Now, had that same file come with some JavaScript on top, and let's look at that slide again. It had a div tag with ID equals target. Had that same file come down with JavaScript, I could grab that node that equaled target. I could create an element, another node, that was called script, and I can embed some content. Nothing malicious in this example. I'm just going to embed an alert box. And then I embed it. As soon as I embed it, it actually gets executed. So obviously, you can see that what's happening here is that I can dynamically change around my, not HTML, because that's static, my document object model, which is the constant memory representation of what's happening in that HTML. So the new DOM looks like this. That alert box got executed. But the HTML document on disk, when it goes down into your cached file, looks absolutely the same. So basic HTML document, HTML body. Again, say there was some JavaScript on the top there, and it just created var text equals alert text test. And I can then call the function eval text. Eval, what that does is it takes its arguments and just executes it like it was a script, like it was just JavaScript or VB, well, like it was JavaScript. So it'll just execute that. It really played the same purpose. The difference here is that the DOM stayed exactly the same. I didn't create a node and embed anything else. And of course, the power of scripting, being JavaScript is Turing complete. You can do, infinity of multiple combinations in terms of how you're going to create that text. That same thing, alert text. I could have just concatenated the string together and then evaled it. But obviously, this is the constant problem with signature analysis, right? I cut up my string as many ways as I want to and in many different ways, and I see how the signature analysis engine does. So let's touch on what the XML HTTP request object is. So this is something that was at first an ActiveX control within IE, then actually became more native. This is an object you can use inside of JavaScript that says, all right, my code has come down. I'm going to create this object called XML HTTP request. Go get the content from the CGI page, and then I can do something with it. But in the background, basically, I can go and fetch content. I can do post and I can do get. Very useful and used almost everywhere in terms of Web 2.0 applications. Even more interesting, actually, though, is something new that's available in IE8 and later versions of Firefox. This is the cross-domain request object. Now, same origin policy said that really we could only go and fetch the content from the same server that our content came from. Well, this is totally different. This is the assumption that I can actually go and contact any domain. And the one detail here is that that domain in its header has to say it's OK that I'm actually going and requesting content from there. But this is extremely powerful. Imagine I bring down content, and then that content is going to go request from any server I want that other content. Obviously, in a mashup, like for good applications, this is what you want. You want to be talking to other cool applications all over the web. That's pretty much all we're going to go over for JavaScript, and that's what we're going to need to talk about script fragmentation. So dynamic retrieval of data. That's what we were talking about with XML HTTP request. So what can I do? Little simplistic example. I do a get with my XML HTTP request, and I have a query string. It just says q equals 2 plus 2, and I check what the response is. 3 lines of code, 4 lines of code. 4 comes back. Simple. But I can actually do dynamic retrieval of data, dynamic question and answers. So what can we do with this in terms of maliciousness? And that's the perspective we're always trying to have. Script fragmentation attack in its basic form. We're going to store malicious content on the server. Now, when we store that malicious content on the server, we're not going to expose it. It's not a web page that you can go visit. It's hidden in a directory that your application can access, but it's not exposed otherwise. The server is going to have a web page. That web page is only going to have a decoder routine in there. So when I'm a user and I go visit a web page, there's basically going to be an algorithm that comes down, and that decoder is going to be use of that XML HTTP request. Once it comes down to the client, the XML HTTP request object requests only a small chunk of that malicious content from the server. So I think we can see where we're going here. We're basically going to be requesting a small chunk. Server in step 4 responds with that small chunk. Next step, the client says, great, can I get another small chunk? And that's going to continually happen until we have everything in place. And as we're getting it back to the client, inside, only in the DOM memory, nothing gets touched on disk here, are we going to have a global variable that's storing all this malicious string, which was otherwise the long, huge, obvious malicious code. Once it gets everything, it's going to execute the resulting code. So it's a little bit more graphic representation. Step 1, store the malicious content on the server. Same way, say I have this is the set slice phone. Say I have that. I download it from Millworm, some generic exploit. I want to test it out. I store that on the server. I basically, and we can see it's got some obvious things that a signature engine would pick up. I send down the decoder routine. What does the decoder routine look like? Well, it looks like something like this. It's basically, you can do it under 15 lines of code, and if you use some libraries, you can do it under that. And it's just making use, again, of the XML HTTP request, fetching the content. It's kind of on a loop time basis, every 2 seconds, every 1 second, whatever you want to do. You can base it off user action. It's really on how hidden you want to remain. I mean, you can do this slowly. If someone's going to stay on a page for an indefinite amount of time, you don't have to go and fetch content every 4 seconds or every 1 second or every millisecond. You can just wait as user actions are happening. Every click, I'll go get 3 bytes or 4 bytes or whatnot. Step 3, the client uses XML HTTP requests. It goes and fetches that content. It says, hey, index.cgi, I want offset 0, and my request length, the number of bytes I want in that file is 3. You can actually specify that. Web server says, great. Goes and fetches it in that file that's unexposed, that's hidden, has our exploit hidden. And if we remember what was in that exploit that we hid on our server, is var space heap spray to address. Probably the most generic type of exploit you can see. It'll send back var. You wanted 3 bytes? I'll send back 3 bytes. Great. Can I get offset 3? I want another 3 bytes. Great. Space HE, which is part of the heap spray to address. And internally, var text is a global memory variable that's hidden inside of the DOM, and it's building up. It's building up as we're asking for offset 0, 3, 6, 9, 12, sending down 3 bytes. Once it has everything, there's 2 methods you can use to execute that code. One is just to call eval. If you call eval, the DOM doesn't change at all. Method 2, which we also saw, was that we can just create an element, script, add it to some node that we'd created, append it. By then, the next step is that it's just going to execute. There's 2 methods, and each of them have their pros and cons. You might want to look a little bit more like a web app. Then you might want to actually use the DOM and change the DOM a little bit more. Also realize that a lot of the JavaScript research tools, they hook document.write and they hook eval. So perhaps by not using eval, that is one way to actually bypass any of the research tools that are being used to try to figure out the obfuscation or try to figure out what's happening in terms of malicious content distribution. So the options for data transfer. Raw, which is what we saw online, I'm just sending down var, I'm just sending down space, heap spray to address, I'm sending it down just in the bytes. I can send it down in XML. XML is cool, it's got all this this language that it specifies what's happening, but it's bulky, right? So we're going to send down more bytes. I could use JSON. So JSON's great. It's JavaScript object notation. It's basically a way that I can send down natively understood JavaScript data. And there's multiple other things that I can do. So if I send it in raw format, we just saw this example. I'm sending down var. If I'm sending it down in XML, data is my tag name, end of file. I have not reached. It's 0. The text equals var. If I'm sending it down in JSON notation, this is the syntax that you'd actually be using. End of file. I can actually include some metadata, which is nice. And in the raw format, You know, I can only guess. I didn't receive anything. Well, it must be done. But if you actually use some type of data format like XML or JSON, you can include some metadata. So end of file is 0 and the text is var. And the way you would use JSON here is that the data would equal eval of S, which was that server response, and then I could just reference that text using object notation, data.text, and I can grab that text, which this first one equals var. So let's talk about, now that we understand that basic attack, let's talk about what's the next step we could even take that. So obviously Flash and PDFs, you can embed JavaScript in there. It's got a certain limitation as to what type of JavaScript you can put in there, but I can put half of my JavaScript decoder in a PDF file, which I could then use between the web page. The more that you can break up the content, the harder it is for anything in the middle trying to bring things together and understand what's going on here. It's going to be. I can also randomize the sequence of offsets. There's nothing to say that I need to ask for offset 0, then offset 3, then offset 6, and so on. Why do that? I'm requesting something. I have intelligence once I'm on the client. I can request object 12, offset 12, and then offset 3, and then offset 0. I can do it in any sequence I'd like to. I can also XOR encrypt the data and include decryption keys. So as I'm sending down each 3 bytes, as we saw in the previous example, perhaps one of the things in my metadata, if I'm using XML or JSON, was the decryption key for the next fragment. So it's that it's really even more difficult to look at or even make sense of what's happening. And this is the more interesting point to make, is that attackers more and more can have use of botnets. I mean, this is like, it's so easy to get use of a botnet for multiple purposes. We saw the cross-domain request object, and what that was I don't just make a request to the object, to the server that I actually came from in terms of my content. I can actually make a request to any single server as long as it allows me to. And if I own a botnet, I'm going to allow that. And so imagine I serve content down to a user, and I make 100 different connections. The content analysis engine sitting in the middle is going to see 100 connections. It's going to have no idea that they are related, and it's all to completely different networks. I can then use, send off saying I want 3 bytes, offset 0 from this host, offset 12 from this host. It can get really confusing for anyone sitting in the gateway as well as the desktop looking at the network. So lots and lots of possibilities of just mixing and mangling and chopping up all my code and asking 1,000 different hosts for all of this. One sec, let me just change my... All right. So let's see if we can see anything. I think the display is a little different, but what I want to show you is this in action. So one of the demos I used here was the Mdac exploit. I don't know if you want to call this an exploit. It's more like a design bug, but it's 100% reliable. Mdac is still and probably will be included in almost every single WebKit until the end of time. It's effective on IE6, but it's a design bug, which means you don't have to do this heap spraying and have like a 50-50 chance that it might work. You just ask it to ask it to execute something, and it will. So let's see if we can get. All right, hang on. All right, so the display, let's see what the display looks like on screen. All right, well, so what happened is that on your right, I put a web page that I went to visit. And on the left, I'm using a tool called Fiddler. It's a simple HTTP proxy. Allows me to see every single request that's actually happening. So I went to go visit that page, and as you probably saw real quick, calc.exe popped up. That's the most common, obvious proof of concept you can kind of show, just to show that you can execute something. Now, in Fiddler, on the left side, or your left, one page came down, exploit5.html. And if we look at that content, which is right here, I didn't use script fragmentation in this example. So this content right here, where I'm circling with my mouse, is what came down. I'm actually, just for the proof of concept, executing a local calc.exe. I'm not going fetching anything. But it's very obvious that with this code, the CLS ID, and multiple other things, that I'm actually trying to do something malicious. Larger chunk of code here. So let's try to do the same thing. This is demo 2 with script fragmentation. So on the right side, again, is a web page that's using script fragmentation. It's a demo, so I've got some buttons that make it obvious that I'm doing script fragmentation. And then on the left side is Fiddler again. So what's happening? What's happening is that it's going to fetch multiple offsets and asking constantly for the next 3 bytes, the next 3 bytes. And for debugging purposes, and so we can see what's going on the right-hand side, as XML HTTP request is constantly asking for those next 3 bytes, I'm showing that file total size is 246 bytes. The end of file has not been reached. And you can see in real time right now, although it's a movie, the text and those 3 bytes that are constantly being sent down. We finally hit 246. Calc.exe popped up on the left-hand side of that screen. You can kind of see it over here. And let me pause the movie for a second. And so what we just saw was probably, 246 divided by 3, whatever that is, like quite a number of requests. So the negative thing here is that with every 3-byte request, we have like 100 bytes. That's the headers coming down. So we're asking for a lot more data, but we're asking it for in smaller chunks. And so it's supposed to be a lot less obvious. But if we're to look the same way we did with the previous example, what we're actually looking at here, my mouse again being circled in this particular area of the content being transferred, file size 246, end of file 0, text :CO4. Imagine some content analysis engine trying to look at that. They're not going to know that that makes any sense, and they're really not going to know what to do with that. So again, no script fragmentation. I ran that simple 100-byte design bug of Mdac through VirusTotal. VirusTotal is always just a real basic way. It's not to say that any of these AVs wouldn't catch it a different way, but it's one of the first kind of ways to check how well they did. And the majority of engines just caught that simple 100 bytes of information to say what it was, what exploit it might be. MS06, 014, that is the Mdac. So simple. With script fragmentation, it wouldn't have caught it. Obviously, the decoder comes down, and no malicious code comes down. It's going to be asked for it in small bytes. So AV won't detect script fragments. The initial page will hold the decoder routine, and then and nothing else. The file on disk will never change. That cache that we talked about at the initial start of the talk, that just held the decoder routine. It never changed. Remember, the DOM maybe changed if you weren't using eval. If you were using eval, it didn't change at all. But the thing is, don't touch disk, don't have it change at all, and in memory, be as specific as possible. It's the end-to-end argument. I mean, that's where the most intelligence is happening, right? It's be as close as you can into the DOM memory. So no substantial content can be scanned as malicious. And with a decoder, so the first thing that comes to mind is, all right, great. So we were catching deobfuscation routines, and that's how we were basing our signatures. I'm just going to try to catch generic decoders. Even if you use, constantly change them, I'm going to start making those signatures for those. Well, it's the same way. I can make them polymorphic, and then what I'm going to start to do is I'm going to try to use as little custom code as I can. There's tons and tons of libraries that are doing this exact same thing. Web 2.0 good applications are doing the exact same thing Script Fragmentation is doing, which is fetching content from servers, and they're going to be fetching content from multiple servers more and more and more. So you've got Prototype, Dojo, Yahoo, lots of other libraries that you can use, and use that code to go fetch these little bytes. Don't make your decoder custom. I mean, that's the #1 mistake a lot of attackers will do. The more custom code they use in anything, malware, malicious web pages, the more obvious it is that we can center on who it is, their technique. Be generic. So use the libraries, less custom code, the harder it is to detect. And at the same time, the JavaScript engines that a lot of gateways are using, can't hold that much state. As I stated at the beginning, almost throughout the entire industry, if you're at the gateway and looking at the application layer, you have under a 1 millisecond to look at content. You really you can't hold that much state. A lot of the public implementations are faulty. Billy Hoffman did a talk in 2008 at Black Hat. He just showed some of the more public tools and showed how they didn't implement various functions and how we could bypass them. I mean, it was just an example of how a lot of the research tools might be lacking, but the private tools are obviously a lot more well implemented. So from the attacker standpoint, it's victory, right? Script fragmentation, very successful evasion technique to evade both the desktop, the traditional desktop, as well as what the current gateway is looking at in terms of, it is still what the normal technique is to send the content all the way through. That's what they're focusing on. They're not yet focused on Web 2.0 applications or attackers using Web 2.0 functionality to use AJAX, in an AJAX-y fashion to send down content. So from the perspective of the attacker, it's very successful. So my final remarks: future defenses, mandatory slide. Sure, better JavaScript emulation, right? This isn't going to help the multiple connections going out, but this is going to be necessary for the other type of future defenses. One way that we combat it and other people combat these multiple connections is perhaps the protection isn't at the gateway. Something based off heuristics triggered an alarm. It goes back to somewhere in the cloud, some central office somewhere, and it gets fed through multiple VMware, multiple Zen machines, looking at what's happening in the DOM memory, looking at what's happening on disk, any changes, looking at what's happening after the fact. Great. You were able to transfer your content from the malicious web server to the browser. But were you careful? How careful were you with your exploit after that? Really, did you use common functions, URL download to file, or something that would be obviously hooked in most kind of desktop research tools? So some type of gateway worker gateway defense combination is going to be used more and more and more, making use of the cloud. So I have under a millisecond to look at the gateway. All right, it got passed. This happens with a lot of DOSing attacks. It got passed. But you know what? We're gonna feed it off somewhere else, and we're gonna catch it on the second one. So it's kind of some type of feedback loop. Gateway client defense combinations. Well, the gateway has a certain amount of intelligence that the client will never have in terms of multiple connections. The client has intelligence that the gateway might never have in terms of bringing that information together. So perhaps functionality within the communication of both the gateway and the client. The other perspective is that right now most desktop AVs, some of them are starting to do some like we did with host-based intrusion prevention systems, some type of exploitation detection in memory. This shouldn't happen, hooking certain instructions, hooking certain functions. But one of the simple things that they could start to do, perhaps simple, even though the APIs really aren't available in all browsers, is to inspect the DOM and the JavaScript engine. A little bit more hooking in there. If they have a closer view of what's actually happening, not just hooking eval and document.write, hooking manipulations of the DOM, then they'll have a better perspective of what's actually happening. You know, one of the latest lucky exploits that I was looking at a few days ago didn't use eval, didn't use document.write. They were kind of concatenating their strings, sending it through multiple functions, would have bypassed any of the research tools that only assume that eval and document.write are the final stages of how you're going to look at that content. So closer inspection of the DOM and the JavaScript engine. And one obvious plugin that I always use is NoScript. I mean, this is more from the perspective of just a researcher or a user. Sure, it's a pain to whitelist everything, but once you do that, you're a little bit better off than you were. You're whitelisting where I allow active content to actually execute, right? That doesn't mean that if I've just whitelisted CNN.com, CNN.com can't have embedded malicious content on there, but there's less of a chance than any given site. It's still the case that given the entire range of malicious websites, 70%, 75% of those are compromised sites that'll send you somewhere else. So sure, CNN.com might have gotten compromised, or some legitimate site might have gotten compromised, but you're going to be sent to another site, and that site is not going to be in your whitelisted set of sites that are allowed to execute malicious actionable content or active content. So that's about it for my talk. If you have any questions, I'll take them now.
Did you have a chance to see combination of HTTPS gets in order to obscure and let the gateway actually not manage to see the whole content?
So you're saying that not only making use of HTTPS to encrypt the communication, but multi-part?
Yeah.
Yeah. I mean, we've seen it. It's the next step. Most proxies these days, they don't fake their cert, but they basically can allow them to be a CA, and if the content's coming down all at once, if it's all HTTP, then they can decrypt that. That's true with most real-time content analysis engines. But doing multi-part, we haven't seen so much. I have seen it a few times, but I haven't seen it a lot. Even the multi-part, it's not common, but it's certainly where it's going. So if we started with the full content coming down, then the next step was multi-part, breaking it down in pieces, and then we have seen it where that multi-part is coming down encrypted. It's going to, if it's not already, and I just haven't seen it, happen where we're just seeing use of a lot more of AJAX-y type communication. So yeah, so definitely it's happening. It's going to happen more. Yeah. Any more questions? All right. Well, I'm here again all day. Any discussions? I'm up for it.
Okay. Thank you, Stephan.